In most of the metropolitan cities of India, a major challenge faced is floods during southwest monsoon. This is mainly because of the lack of proper management of stormwater. In hilly regions as well, or in Deccan Plateau or Western Ghats, the possible failures of landslides can be reduced. The risk of failure of the slopes can be reduced to a greater extent by proper management of runoff, especially through drains. So the first step involved in the design of drains was the estimation of peak flow. Okay, if we have a mean average this much quantity is expected to run off, and if we are designing the channel for that, when maybe once in 100 or 200 years this peak flow may be reached, but at that time this can be insufficient. So if enough financial status is there, it is recommended to take peak flow itself. Now, how to estimate this peak flow? Several scientists have prepared empirical formulae for that, like Dickens formula, where Q is the expected peak flow, C is the coefficient depending on the drainage or catchment characteristics, like it depends on the infiltration capacity of the soil there, the cultivation type used there, permeability, etc. C, and it depends on the catchment. Now A is area of the catchment receiving rain in kilometer square, and Q will be getting in cumex. So Rives formula. Now this Dickens formula is commonly used in northern India. Next is Rives formula, which is C dash A raised to 2 by 3. C dash is the coefficient that depends on the catchment. A is the area of the catchment in kilometer square, and in this is not English formula is used in southern part of India. It is 123 A raised to half, where A is the area of the catchment. Next, estimation using rational formula. This is nothing but we'll be taking critical intensity of rainfall multiplied by the area of the region. So this PC is critical from this we will be having critical intensity of rainfall, or from this we will be taking critical depth. So PC is critical intensity of rainfall in centimeter per hour. Okay, centimeter per hour. And area is area of catchment in kilometer square, and K is that percentage of the rainfall which will be turned into runoff, and it depends upon the characteristics of the catchment. Means like infiltration and such property. So we have a particular percentage which is a characteristic of that catchment. Now estimation of discharge using probabilistic methods or statistical methods. Direct method. So direct method means We will be considering return period of a particular peak flow. We will be taking this PC itself. Suppose we have the rational formula as KPCA by 36, where PC is the critical intensity of rainfall in centimeter per hour. That particular value can be chosen using probability. That is, it is expected to occur a maximum amount of this much rainfall once in 100 years or once in 50 years. Suppose we have in a particular catchment 1.2 centimeter per hour is expected to occur in 50 years, or 3.6 centimeter per hour. So another maximum is also observed. Means after this many years there is an frequency. We can observe the historical records if we can check and find out that a particular intensity of rainfall will repeat after this many years. That is the system in or 200 years something. Suppose we are building drainage for a metropolitan city, means where this flood or such critical conditions are there, we have problems arising, and we are going to provide maximum amount of money into that. Anyway, by any means we have to remove that problem. In such cases we choose this return period, a higher return period, so that maximum rainfall is taken, maximum peak flow is taken, so the design dimensions of the drainage will also be high. Okay, that is return period. Now another thing is Gumpel's method. So next method which I have told was Gumpel's method. In Gumpel's method, this particular intensity is that value. If we have a past history of some values, take the mean of that values plus k times standard deviation. So we'll be taking a history of values for a particular number of years, find out the mean, standard deviation, and the chosen peak flow is given by this equation, where this k is given by where t is the return period. So ln 1 by t, that is the Gumpel's variable, negative of that value, so as to get a positive value. Okay, next, that is Gumpel's method. Next is direct method. Though it takes some time, it is the most reliable and accurate method of finding peak discharge. So what we are doing is, from the meteorological department we can get unit hydrograph, which is a characteristic of the catchment. Okay, unit hydrograph. I think so obtain peak discharge from flood hydrograph via unit hydrograph of the region available. So unit hydrograph of the region may be available with meteorological department, plus we have to get the how this unit hydrograph is obtained. They will have past records of rainfall depths measured, and intensity of rainfall. Let's explain that anyway, since we got into the term unit hydrograph step by step. What they can do is we can obtain hydrograph, which is intensity of rainfall, which is a graph showing intensity of rainfall with the time. intensity of rainfall. How this intensity of rainfall is obtained? Say for 1 hour this much depth of precipitation has occurred. Then that ratio can give you the intensity of rainfall. So that is how you get hydrograph. We can record this. We have the rainfall gauges at locations at locations like open spaces, and nowadays we have direct computer systems to measure the intensity of rainfall. Anyway, we have to get hydrograph first. Then multiplying this with area will give you. Before that, this is what rainfall occurred. Now we have infiltration index or W and W index. This infiltration index takes into account only that amount of water which has infiltrated into the ground. Now this W index will include with it that amount of water which has infiltrated or penetrated into the ground, as well as interception losses, etc. So these are intensities only, means centimeter per hour or meter per second, like that. Okay, with per unit time. So what we can do, if we have some depth of precipitation measured by the meteorological department minus this 5 index times for whatever time they have measured this much depth will give you the total runoff. That is, if you have the depth of rain occurred as P minus W into T will give you the runoff. That is what I have meant. Okay, now remove all these things. So this multiplied by area, this intensity multiplied by area will give you some meter cube per second, Q max. Okay, this is intensity of rainfall. You have to first reduce this W index from this W. So what I was telling, hydrograph only. When you are subtracting W index, you will get whatever runoff there is. So multiplied by the area will give you hydrograph. So this is runoff with respect to time. Now one more thing you have to notice, the initial surface runoff will be that water already stored in the depression. So we call it as base flow. You have to subtract base flow as well from this, or base flow, and after subtracting this base flow you will be getting direct runoff hydrograph. Direct runoff hydrograph. So due to that rain, what much flow is occurred? Direct runoff hydrograph. Now this is for an effective precipitation of this much centimeter depth. So for 1 centimeter occurrence of rainfall, what you have to do, divide all these coordinates by the depth of precipitation. So you will be getting some unit hydrograph. The area of this will give you 1 centimeter. I think you are okay with unit hydrograph. Now it is a characteristic of the basin. We are considering this as a characteristic of basin. So to obtain flood hydrograph for a particular year, you have to first take this unit hydrograph, then multiply each coordinate with the effective depth given by the meteorological department. Now this depth should be what? This depth should be taken after subtracting. Before multiplying unit hydrograph with the depth, make sure this depth we have subtracted this losses, because when we have drawn unit hydrograph, we have neglected that losses. So make sure when we are multiplying, we are going to the reverse process. Okay, multiply to get this. Now to match with the duration, what you have to do? If this unit hydrograph we have or available with the meteorological department is 4 hours, a 4-hour unit hydrograph is what with the meteorological department, what you have to do is after 4 hours again draw the same unit hydrograph. So suppose the duration we want is 8 hours, the same can be drawn. So this will whatever depth is recorded for first 4 hours, multiply the coordinate with that depth. Next 4 hours, multiply the coordinates with that depth. Then what you have to do? Sum up this and this and this. So sum up all the coordinates to get the new hydrograph. See the new, which is the flood hydrograph we require. It is direct runoff hydrograph only what we require, and the peak value will give you peak flow. So what we require is direct runoff hydrograph only, and the peak value is what we need. Now the location. If the location of available unit hydrograph is different from what we require, just do routing. That is what in the previous slide I have told you. If the hydrograph available is that of an upstream point, transfer it using routing techniques. What is meant by this routing? There are different routing techniques, one of which is Muskingum routing technique. It is simple theory behind this. Inflow to that point we require minus whatever depression storage at that point take place as outflow. So from the beginning, or from where we have from the catchment, suppose the meteorological department has unit hydrograph of the catchment, from that do this, I minus delta is equal to T. So divide by T. This is the basic principle behind my routing. So I by T means it is meter cube per second what we are getting. So inflow minus outflow will give you the depression storage rate. Do that up to the point. Next, so this is the way we find out peak flow. Now decide on type of drain. So the drain can be surface drain, subsurface drain, open drain, closed drain, or based on the type of the pipe we use, lining we use. So all this depends upon factors like financial status, See, closed drain is much costlier than open drain because maintenance required is very high. Plus, the material required for construction is high. We have to check for corrosion. These manholes are required at a spacing of 3 meters. That depends on the diameter or dimensions of the pipe. Next, this infiltration characteristics of the soil. So that determine whether you have to use surface or subsurface drains. So there are several factors. Based on this and the financial status you can determine. Next is we are going to the design section. How to find the dimensions of the pipe? Use Manning's equation, which is nothing but Q equal to 1 by N R raised to 2 by 3 S raised to half multiplied by area, where N is some coefficient, Manning's coefficient, that depends on the surface of roughness. A is area of cross section. Okay, area of cross section of the drain, and R is hydraulic radius, which is given by ratio of area of cross section to the wetted perimeter, and S is slope. Either you can design the slope or you can adopt the natural slope. See, if the slope is too high, in many areas you might have seen the slope is too high and the erosion, there is a risk of erosion. This is a type of drain which can be adopted, step by step drain. Okay, now this surface, it can be perforated. If it is not combined sewer, perforated drains are preferable. Like you can use gravel or some filter type material as lining other than concrete pipes or concrete permanent lining. You can go for that, and make sure the water percolates to, and if it is fresh and clear water, you can make its path to aquifer. So just keep all these points in mind. Next, parameter and depends on surface roughness. See, if fine sand, colloidal sand is on the lining, it is 0.020, and if cobbles and shingles 0.0, as roughness increases, parameter and value increases. So, and from the equation we have Q, the peak flow. If we want to find the dimensions, you can use area and R. And while moving forward with the calculations, if it is circular cross section you are assuming, you will not find any difficulty. But if it is rectangular or some other calculations, you may find some difficulty. So what you have to do, assume the depth, drain depth based on this. Okay, it depends on the permeability of type of soil. Is to check whether velocity is not less than self-cleansing velocity. In case of, okay, what you have to do is with this is, if the channel is erodable, see the shear stress, we are considering some slope and a particle like this. Okay, see, non-erodable, I mean concrete lining channels, if sediments are getting deposited, there it can cause blockage. So either you can use the Stokes slow velocity, you have the terminal velocity there, that is the vertical velocity of the particle only, there you find, I think, in Stokes law we have the vertical velocity of the particle, and I think the velocity of the particle should not be less than that value. Take care so that no deposition. I think the Stokes law, the velocity is given by some 2 by 9 d 2 by 9 and d square into 2 by 9 d square by nu into rho sediment minus rho w times g. Okay, now another thing is this particle, it experiences weight times slope, and the shear stress is the factor that holds behind it, tau r is known. So this should be high so that it moves with the flow. Okay, based on this and this natural flow Chassis equation, which is another equation like Manning's equation only, to describe open channel flows. Combining these two factors, another equation is there like V equal to, which is of much importance than this, root of 8 beta by F into gs minus 1 into d, where this d is the particle size only, gs is sediment specific gravity, beta is a constant coefficient, depends on roughness only, just like we have our parameter n. Then this f is friction factor. So this velocity should not be less than this value. Just take care of that while moving with the design. And next is drainage spacing from drainage equations. Okay, how in roads, if you are checking, if the rainfall is that high that even lateral drains are there required, that is like this. Okay, this spacing, or if we have closed drains with openings at this much spacing, so this spacing depends on what permeability, how water reach the drain, and the water flow takes place how. So so two factors are there, permeability and water flow takes place based on hydraulic gradient. From higher potential to lower potential water flows plus permeability. Okay, so we have Darcy's law, which connects these two factors, that is velocity of flow is proportional to hydraulic conductivity, where K is permeability only. Okay, so based on this, Hookout has obtained this equation, that is L square equal to 8K d naught H by Q plus 4K H by Q in case we have impermeable, in case the drains reach impermeable layer, that is the water is drained to some impermeable aquifer using vertical drains. In case they do not reach any impermeable layer or flow horizontally, you have to use the equation L equal to 8K dHQ by Q plus 4K H square by Q, where K is the permeability, D naught is the depth. Now Q is Q by B, per unit width flow. Okay, H is height of the drain. So I will show that figure to you. So this clearly explains. CQ water flow takes place into the drain vertically. That is permeability only shows. L is the drain spacing. See, permeable water penetrating like this. Here also some water penetrates. And D naught is the depth of aquifer from drain level to impermeable layer. That is, from the drain water is removed to the aquifer impermeable layer, so that water drain gets cleared and next it is ready for supply, it is ready for gaining water again. That depends. So how fast the draining takes place, that is how drained off. If an impermeable layer is nearby, see, more amount of Q can be supplied. That is why D naught is depth from drain to impermeable layer. H is the depth to water level. That is, H is the mid-drain water table. Above drain, how much water can be collected.